Welcome to the Running the WRF model talk. Before you go through this talk, you should have gone through the talk on running the WRF preprocessing system, which explains how you would prepare data for a model run using real atmospheric data. It may be helpful to download the WRF model code and follow along. Write down the questions you have while listening to the talk. This schematic shows the basic workflow when we are making WRF runs. The WRF model code actually has two main programs. One of these is for producing initial and/or boundary conditions for the WRF model, which we refer to as initialization program. And the other is the WRF model itself, which carries the time integration. If we're running the model for real atmosphere, we will first run the 3 WPS programs and prepare domain and meteorological data for the model. We will then run the program real.exe and followed by the model itself. There is another way to run the model using idealized initial conditions. This is through the idealized initialization programs. These are the topics we will cover in this talk. We will first show how we can make some model runs. We will then talk about some basic options, and these are options we set at the runtime. It will be followed by topics on checking the model output and learning to do simple troubleshoots. We will be focusing on a single domain run in this talk. The nested domain run will be covered in another talk. Before we start to run the model programs, the first thing to do is to check if we have the executables we need to run the programs. Here we skipped the compile step, which we will be covered in another talk. Assuming we have compiled code successfully, the WRF executables will reside in WRF main directory after compilation. Depending on what we have chosen to compile, real or idealized initialization, different initialization executables will be produced, and these are either ideal.exe or real.exe. The model executable WRF.exe is always there, and the same for both real and idealized cases. The two utility programs will not be discussed in this talk. If we're running real atmosphere simulations, we need first to run through the WPS programs and produce output files for a few time periods. Remember, we need data to provide lateral boundary conditions for the entire simulation time. WRF model has a number of provided idealized cases, and these include flow over hill, sea breeze, supercell, baroclimatic wave, and large eddy simulation cases. They are showing on this slide. The model can be run in 1, 2, and 3-dimensional spaces for these idealized cases. However, the most popular use of the model is the real data simulation in 3-dimensional spaces. We are going to show how to make a real data run, as well as an idealized case, the supercell case. This slide lists the steps to run the model. First, change directory to run or one of the test case directories. If we are running the model for real atmosphere, we'll make the files from WPS available in the working directory. This is done by moving or linking the files from the WPS directory. Next, we will need to edit the namelist file for runtime options, and this includes simulation times and domain informations. Once we've done so, we can start running the initialization program, either real.exe or ideal.exe. And the final step will be running the model executable itself. Here is a look at the model directory run. It contains mostly files used for model physics, such as radiation and land models. It also contains README files for runtime options and a few other things. This is the look of the directory before the model is compiled. After the model code is compiled, the model executables are created, and these executables are symbolically linked to this directory. Also, a namelist.input file will appear, which may be copied from the test.emreal directory or one of the idealized case directory. This is for us to edit if we decide to run the model in this directory. Now we are going to talk about how one would make a work model run for a real data case. Let's choose test.emreal directory for our model run instead of the run directory. Taking a look at this directory, we should see the physics data files are symbolically linked to this directory from where they reside in the run directory. The model program executables, real.exe and wrf.exe, are also symbolically linked to this directory. We will also find the runtime option file, namelist.input, which we will edit to match the domain and the data we pretend we have created. To simulate the real atmosphere, we must first run WPS programs and process data for the model run. We need data at some time interval to cover the entire simulation period, whether it is 24 hours or 10 years. We need to make the data available in this directory. We can do so by moving or linking the files to this directory. The command shows how the files are symbolically linked to the current directory. The option is -s here. The next step is to edit the runtime option file, namelist.input. Since our first goal is just to get model to run, a minimum set of options to change is start and end simulation times and the model grid dimensions. We may also need to change the input data information, such as input data frequency, as well as the number of vertical levels in the input data. For example, the GFS data today has more vertical levels than that data just a few years ago. Then we can run the program real.exe to produce initial and boundary conditions. The way to run the program depends on how we compiled it. The most common way to compile the model is to use MPI, which stands for Message Passing Interface, or DMPAR as we sometimes refer it. Here, DMPAR stands for Distributed Memory Parallelization. MPI would allow us to use multiple processors across many computer nodes. The way to execute an MPI job can vary from different MPI implementations, but MPI run is a typical one to use. This is shown here, where capital letter N is the number of processors to use for the run. For real.exe, typically we won't need a lot of processors for the job. If it is successful, running real.exe should produce two output files, with input D01 with BDY D01. The first part of the file names tell us the type of data the file contains, and it has its domain association in the file names too. The WRF input file contains atmospheric data as an input to the model at the model start time, while the WRF BDY file contains data along the model domain lateral boundaries. The WRF input file has atmospheric conditions at a single time, and the WRF BDY provides atmospheric conditions along the lateral boundaries and for the entire simulation period. This schematic is just a reminder to us as why we needed the lateral boundary condition. We can see the available times in the WRF BDY file by using the netcdf2 NC-dump, like what is showing here. Here is an example of the time output by issuing the NC-dump command, NC-dump -v times. If we prepare data for a 24-hour model run at a 3-hourly interval, we will have 9 WPS output files. With that, we would be able to produce a WRF BDY file that contains 8 available times. This is because these times only represent the beginning of the available period where the lateral boundary condition applies, and each valid time also has information about how the boundary values will change in the 3 hours ahead. This is also a good check to make sure the program real.exe is executed successfully. Once we know the initialization program has worked correctly and the WRF input and the WRF BDY file have been created, we can move on to run the model program. Like the initialization program, how we run the model would depend on how we compiled it. Again, the most common way to compile the model is MPI, and hence the command to run the model is MPI run. Typically, we would use more processors to run models than the initialization program. If we are successful, the run should produce one or more WRF history files, such as one showing here. WRF out D01 plus some time information. The history files are the most important output from the model. It is the solution of the model integration. We may also find a file named WRF RST. This is a model restart file, which can be used to continue a model run, provided we have boundary data that covers the remaining simulation period. You may wonder what determines the time that appears in the model output file. It comes from the start time in our nameless.input file. The model output file may contain one or more time periods, which can be controlled by the namelist. We will cover that when we explain more about the namelist. The WRF restart file only contains one time period, and it is valid at the time showing in the file name. As it happens, this case date is for the 2005 Hurricane Katrina, and the image here shows a WRF 4-kilometer simulation of the storm at the landfalling time. Next, we're going to describe how to make an idealized model run. Information about each of the idealized cases will be explored in another talk. In contrast to a real atmosphere initialization, an idealized case represents the initial atmospheric flow in a simplified form. For example, the flow can have zero velocity at the start time, or there is no temperature variation in horizontal except for perturbations, and so on. These flow conditions can be coded in the initialization programs. These idealized simulations are aimed to study certain flow characteristics and help to explore dynamical and physical mechanisms that operate in the real atmosphere. To run the model using the provided idealized initial conditions is trivial. Mirroring the real data run, we would choose to compile the model for an idealized case, and this will create ideal.exe for model initialization and the model executable. When we compile for different idealized cases, the difference is only in the initialization program. The model executable remains the same for all cases. Similar to the real data case, these executables are symbolically linked to the run directory or test case directory, and one can use either directory to run the model. Let's choose the three-dimensional idealized case EM²SS. This is for a supercell convective storm simulation. The quarter here refers to the environmental wind that makes a quarter circle when plotted on a hodograph. Let's change to this test case directory. Here we should find these files among others. The README file has some case information. The input sounding file is a text file which specifies the initial atmospheric wind, temperature, and the moisture profiles. We also see a file named runmefirst.csh, and we would run this file to link physics data that might be used by this case. As it turns out, this case by default only uses warm ray microphysics, which doesn't require any physics data files. This is another characteristic of an idealized case simulation. It often uses only a subset of physics or no physics sometimes. Moving ahead, we will now run the program to create initial condition for the model. Simply type ideal.exe to run. Most of our provided idealized cases have small number of grid points, which we can easily run just using one computer processor, like what we do here. For many of the idealized cases, the input is just a sounding, such as in the supercell case. The most complex initial condition is the one for the baroclinic wave case, which specifies a two-dimensional jet feature in its initial conditions. Running the idealized initialization program only produces an initial condition file, WRF input D01. Because these are idealized flow conditions, there's no need to know anything outside our simulation domain. Hence, a boundary file is not needed here. The model would still require data at the lateral boundaries, but they are handled in the code. How it is handled is a runtime option one can set in the namelist file. For the east-west boundary conditions, these are the options: periodic, symmetric, and open. The supercell case uses open boundary conditions in both x and y directions. After we create the initial condition file, we can move on to run the model. Again, because the number of grid points are small in these idealized cases, one can run the model using just a single processor or with just a few processors. The model output file from many of the idealized cases, though, is still worth out, but they don't have a real date in the file name. This is because an idealized case doesn't require a real date, and the start time in the nameless file is often set to year 1, month 1, and so on, as reflected in the file name. This is showing here on this slide. If an idealized case requires radiation physics, then a proper date specification may be important. The image on this slide shows a three-dimensional plot of the simulated supercell at hour 2. The next topic for this talk is to go through some basic runtime options. Before we go through some of the runtime options, we will just say a few words about them. A runtime option is an option that can be read in by the model during its execution. It allows a user to change model options without the need to recompile the source code. The Fortran nameless construct is used for the runtime options. A namelist can have a name, and it is bracketed by ampersand and a backslash. In the WRF model, multiple namelists are placed in a file called namelist.input. A variable in the namelist can have a single value or an array of values. They can be integer, real, or logical, and these are all defined in the code. So when we are making changes to a namelist file, it is best to follow the existing format. A single value often means it is used by all domains, and multiple values are intended for individual domains. A typical namelist.input file will have these namelist records: time control, domains, physics, dynamics, and the BDY control. We will call the first two essential, since this needs to be modified for every case. Once we are more experienced, explore the others, and options for physics and dynamics will be covered in their respective talks. The first nameless record we are going to talk about is time control. Here is a partial list of the options in the record. The first column of the namelist applies to model domain 1, and hence They will be the focus of this talk. The grayed out ones are options for nested domains, which will be covered in another talk. Note that some have single values and others have multiple ones. This group of namelists set the model start and end times, the input data interval, and the model simulation time. The start and end times are used by program real.exe to create initial and boundary condition files. The runtime variables can be used to set model integration length, but one can also use start and end times to control the simulation length if the runtime variables are not set. The input data interval is set by interval seconds, which should match the same variable in WPS. The history interval option sets the interval at which model solutions will be written into a file. The frames per out file option lets you set how many model output time periods will be written into a single file. The restart interval sets how often you would like to write out files that will allow you to restart a model. The restart option itself sets the model for a restart run. Here are a couple of notes on history interval and history files. It is best practice to choose a model integration time step, which will be discussed a little bit more later, that can be wholly divided by the history interval, so that you can always get the model history at the desired time. The timestamp in the history or WRF file name is the time when the file is first open for writing. One can write a single or multiple time periods of model output in a WRF file. The data written into the history file is snapshot of the model atmosphere at the time of output. Here we have two examples on how we use frames per out file to control the history file writes. In the first example, when a large value is used for the option, a single WRF file will be written, which can have up to 1,000 time periods in this history file. In the second example, we set the value for frames per out file to 1, and this will result in multiple WRF files. Each now will contain only a single model output time. Depending on what is convenient to you, you can choose how many time periods you would like to write in a WRF file. Here are a few notes on restart interval and a restart file. The time unit for restart interval is minute. By default, a restart file will not be written at the model start time, a trivial point perhaps. Unlike the history file, each restart file only contains one time level data, and its valid time is part of the restart file name, hence easy to find. The size of the restart file is quite a bit larger than its history file counterpart. And the purpose of the restart file is for restarting the model only nothing else. A few more notes on the restart. It is important to know that a restart run is just a continuation of a model run. If you like, we can think of it as checkpoints of a longer model run. Why do we need it? Suppose we would like to make many years of model simulation, or a simulation with very high model resolution. Both can take a very long computer time to complete. And the computer we have access to limits the wall clock time each user can use at any one time. The restart capability would then allow us to complete our model run in several pieces and ensures the solutions are identical whether we run the model in one shot or multiple ones. How do we make a restart run? First, we must make a model run that writes out a restart file. When we make a restart run, set the nameless variable restart to true, change the start time variables to the restart time, and modify the runtime length. There are a few other things in the time control namelist record. This group specifies the data format for history, restart, input, and the library boundary files. The WRF model supports a few data formats, which include binary and a group. But by far, the most common format used is netcdf. In case we're going to work with a very large model grid, 1,000 grid points or more in each direction, a good way to write restart file is to set the I/O form value to 102, which tells the model to write one file per processor. Since the purpose of restart is just to run the model continuously, it makes both write and read faster because of the smaller file sizes and the more processors used to write and read them. Now we're going to talk about nameless record domains. This slide shows a partial list of the variables in that nameless record. MaxDom. This variable defines the number of domains we run the model with. For a single domain run, this is set to 1. The next three variables set model grid dimensions. The first two are the horizontal dimensions, which must match what we set in GeoGrid. The vertical dimension, evert, is a model parameter, which we define when we run the program real.exe. The next two variables are dimensions from the MatGrid output data, and hence must match the values from the data file. Non-MatGrid levels is the number of vertical levels in the input data, and non-MatGrid soil levels is the number of soil data levels from the input data. We can use NCDump to find out these numbers. Continue on. Here, dx and dy are grid distances in x and y directions, and they must match those defined in GeoGrid. In most circumstances, dx and dy are the same. Time step is an important parameter for model integration, and it is defined as an integer. It sets the time interval the model solves its equations. How big a value we can use for time step is determined by the numerical analysis of the model solution method. In real data applications, It depends mainly on the grid distance of the model. It can also depend on how we configure our domains, such as map projections and distribution of vertical levels. The atmospheric flow condition can also impact the time step. The rule of thumb is 4 to 6 times the grid distance in kilometers. For example, for a 30-kilometer grid model, we can use up to 180 or 6 times 30-second time step. Incorrect time step value can lead to bad model solutions and even model blowups. We will learn more about this in the dynamics talk. If we choose to use fractional time step, they must be specified as integers using numerator and denominator separately. Defining time steps with integers will ensure accurate time tracking in the model. The last variable on the slide is the model top pressure in unit of hectopascals. Make sure the data processed in MATGrid has data at this level. 5,000 hectopascals is the recommended lowest model top, which is about 20 kilometers high above sea level. The last variable in the namelist record domains we may want to edit is data levels. While the variable evert sets the number of model vertical levels, the exact levels or the distribution of the levels can be set by this variable. For example, how close to the ground the first model level is, and how thick the vertical layers are, and so on. If it is not set, the program real.exe will compute a set of levels for you, which may be a good approach for the beginners of the model until we gain more experience with the model. We've covered the essential namelists which we must change for each case we run the model. Here is another namelist we may want to consider, which is about the lateral boundary zone. Spec BDY width is the number of grid points where forcing data applies in the model. The type of boundary condition is specified, and this is for real data. The figure illustrates how the forcing data is specified in the boundary zone. The outer row and the column uses the forcing data completely. Then the next 3 grid points will have weighted forcing data and model data until it hits the last grid point in the zone, where the model data is fully applied. 5 rows and columns are typical values used, but wider width may work well in some cases, especially when forcing data has much lower resolution. There are other nameless records we may want to get familiarized with as we go. These are nameless records physics and dynamics. We will learn more as we go through physics and dynamics lectures. Where should we start when we first begin to use the model? To help us out a bit, the model has many nameless templates available in the test directories. For example, in test EM real directory, we have a nameless template for a model of 4 kilometer grid size, something for 10 kilometer grid size or 30 kilometer grid size. Always start with one of these name templates. We will always need to change the date, the grid dimensions, probably the input and output intervals, but The physics and the dynamics options from this template should generally work well for applications of similar model resolutions. You can also check out the options we use in our applications, and they are documented in the user's guide, which is available online. The web page is provided here. If you'd like to read more, you can find more information about the name list options in these documents listed on this slide. It is important to understand the options before we would like to use them or modify them. So far, we talked about running a model job within the WRF code directory structure, but we don't have to. Once the code is compiled and the model executables are generated, we can run the model executable in a totally different directory. We just need to make sure the input data, the physics data files, model executables, and the name list files are available in the new directory. We can imagine a scenario where we keep the compiled code in one place on our HPC, but we may want to make multiple model runs in different locations on the disk. Next, we're going to talk about what to look for once we've finished running a model job. After a model run, the run directory will have many new files. First, we should have some RSL files. Even if the model fails, we should still get these files where we may find clues as why the model failed. If the model run is successful, we should have one or more WRF out files. If we set restart interval small enough, we may also get some restart files. Depending on the number of processors we use for an NPI job, we should get that number of rsl.out and rsl.arrow files. In this example, we use 4 processors to run the model, and therefore we will get 4 pairs of rsl.out and rsl.arrow files. Under normal circumstances, the 0000 files, the leading RSL files, will have the most information. If a model run fails, then error messages can appear in other files. What should we be looking for in a standard out file? Type tail on the leading RSL file, and we should see the message success complete WRF if the model run is successful. If we don't see this message, it probably means the model run has failed. In this case, we should look at the RSL files more carefully and look for error messages. Now, how do we do a quick check on the model history output files? First, list the files. They should have many hundreds of kilobytes in size. Make use of netcdf to ncdump. We can check any variable in the file with this tool. Just be aware to check any model field. It could be a lot of data. The best tool we have is called NCView, which is a netcdf file viewer. It is a good tool to do a quick scan of the data files. And this is not just for WRF model output. We should use it for any netcdf data files generated from various WPS and WRF programs. Once we are convinced the data is good, we can then proceed to make some better plots using a graphic tool. What can we find in a RSL file? We should find model versions listed, how the model is partitioned in a NPI job. In this example, it shows the model used 2 processors in X direction and 4 in Y direction for a total of 8 tasks. We should also find prints on the time taken to run one model time step, as well as time taken to write history or restart files. If the model encountered problems, some prints or error messages may appear in the RSL file too, like the one showing here for CFL. What about fields in a WRF-out file? A typical WRF-out file will contain 1, 2, and 3-dimensional output fields. The meaning of the fields can be found by using NC-dump to output the list of fields in the file and look for description for any particular field. For example, we can find the description for field T as perturbation potential temperature theta minus T0. So we know the field T isn't temperature, but potential temperature minus a constant. And the constant happens to be 300. Note that the model output fields are typically instantaneous, and the actual file size will depend on the model options used. Some options have actual output fields. The last topic we will cover briefly is to learn to do some simple troubleshooting when a model program fails. One of the easiest mistakes we make is to make a mistake in namelist.input file. Unless the option has a specific check in the model, the general error message one gets is like the one showing here, error while reading namelist. But it tells us which namelist record we had error in and provides a guess on which variables that could be in error. This is showing in the first example here. It tells us the namelist record dynamics may have at least one error, and the options scalar ADV opt or GWD option may be in error. It turns out the option GWD option is misspelled here. The correct spelling is GWD opt. In the second example, the input data dimension and the dimension we entered in the namelist file are checked against each other. And hence, it prints out this special error message for us. If we read the message carefully, we can probably understand what it tries to tell us. Both of these types of errors can happen when we run initialization program as well as the model program itself. One common failure of the model is segmentation fault. This generally means there isn't enough memory to run the job. If we are trying to run the model on a small computer with limited memory, we may get this error. This can be corrected sometimes by typing Unix command unlimit if the computer actually has more memory that can be used. If this doesn't help, it means we will need a computer with more memory, or we can decrease the model grid dimensions to reduce memory use. On a HPC computer, we may still get this error if we don't use enough processors to distribute the memory for the job. Another common model failure has to do with breaking the numerical stability of the model, or the CFL condition. If we find many prints in the RSL file that look like this, it means somewhere in the model the stability condition has been violated. The prints do provide us the grid locations where this happens. If the condition persists, the model can abort. A common solution to this problem is to reduce the model time step. If it doesn't help, there may be more serious problem with the data and/or the model configuration. We are now reaching the end of this talk. You can read more about what we covered in this talk from Chapter 5 of the User Guide, which is available online. This talk should be helpful for the first exercise case you will be doing on the first day of the tutorial. Thank you for listening, and make sure you prepare questions for discussions during the actual tutorial.